Okay, so we're going to move over to the gas PVT properties, and let's just say that we're at a temperature. Of course, we have to keep that constant. And let's just say that this gas that we're looking at used to be together with this oil. Okay? Let's say that they were in equilibrium. But we basically took away the oil. Okay? So now we're all that we are left with is this gas at pressure that's at the dew point. Okay? We've taken away the oil that used to be in equilibrium with the gas. I'm just going to get rid of it so that we don't confuse ourselves here. So we're left with this gas at the dew point pressure at temperature T. We take that gas to the surface through a surface process, whatever surface process you want to use, two-stage separator, three-stage separator, single-stage separator, whatever you like. I'm going to call this capital P. That's my shorthand for surface process, okay? Just whatever you want to put inside. The point is that you go in with something and you come out with a surface gas and a surface oil volume. The ratio, because this happens to be a gas we're putting into the process, we get a surface gas volume from a reservoir gas and a surface oil volume from a reservoir gas. So we're going to get, the nomenclature should look something like that. Okay? This basically is reflecting our composition of the gas. Okay, it's a volumetric ratio, but it's kind of our gas composition, approximately. It's the gas formation volume factor is going to be defined as the gas volume at the pressure. Oh, it's too small. I realize it. Just get rid of this. The gas volume at temperature and pressure divided by what we end up with as gas at the surface. Okay? It's called the gas volume factor. Okay. And then while the gas is down here at temperature and pressure, we can measure its viscosity, okay? Or calculate it at temperature and pressure. That pressure where we can measure or calculate gas viscosity would be at any pressure greater than or equal to the dew point. Okay? If we went to a pressure below the dew point, what would happen? It wouldn't be a gas. It would be a gas and an oil. And you can't really measure the viscosity of this gas and the oil together. Okay? So we're going to restrict our viscosity to pressures that are greater than or equal to the dew point. Okay, and what is the dew point of the gas? Well, it's the pressure where it used to be together with the oil. Okay. Should I go ask them if they want to join? You know, they have the expression, curiosity killed the cat. They have no idea what they would be doing if they walked in here. So. Okay, now I've got a question for you. If we take this gas to the surface like we were talking about here, if the pressure that if we start at a pressure equal to the dew point and we get a value, I'm just going to give you some numbers now. That'll be comparable with the previous example. Let's see, 100, 500, 10 to the minus sixth, standard cubic meters of surface oil, okay, per standard cubic meter of surface gas. Okay, that's probably a reasonable number at 300 bar. Okay, so let's just say this. Let's say that at the dew point pressure was 300 bar. Okay. Now, for the sake of argument, let's just say that I take this pressure here in the cell, in this PVT cell, to 500 bar. But I take it to 500 bar after I take away the oil. Okay? I'm just left with the gas, and I increase its pressure to 500 bar. Okay, right? I put it through the separator. I put it through the surface separation process. What is going to change in the surface volumes? What is going to change in the surface volumes? Now, I have to be a little careful here. The volume of gas here, that's going to change, right? Because we've got so many, we've got the container full of gas. It's, I don't know, 0.683 moles or something, and it's like 100 cc's of gas at the dew point. Now we raise its pressure, so the 0.63 cc's is going, or no, what did I say? 100 cc's is going to get smaller because we compress it to 500 bar. So now the volume is going to go from, see, the volume at the dew point was 100 cc's, and the volume now is going to be, I don't know, 60 cc's. Okay? Something like that. But my question is, what happens to the volumes at the surface? And don't answer, just think about it for a second. Okay? Just think about it. Don't answer me. The gas volume at temperature and pressure changed from 100 cc's to 60 cc's, going from 300 to 500 bar. And the question is, what is the ratio of these two volumes? Is it going to change or not? And I'll just do a raise of hands. How many think that it will change? How many think, yeah? Be honest. I mean, it's like being wrong is not, okay? Okay? And how many think it won't change? Okay? So at least there's a state of uncertainty, which I expected, which it's not. Now, the thing is that the amount of material we put into the surface process, moles or mass, does it change? No. So the moles going in, this is kind of like a well stream, the moles going in does not change. The composition, does it change going from 300 to 500 bar? Does the composition change of what we put into the process? No, because it's gas. I mean, we took away the oil. So we're just left with the gas. We bring the gas to a higher pressure. The amount of gas is the same. The amount we put through the surface process is the same. The composition of what we put into the separator is the same. So the moles and the composition are the same, what we're processing. How can it change the products? I don't think it can change. Because the products, the amount of the products is only a function of how much we put into the separator, right? And the composition of what we put into the separator. And both of those are remaining constant. Okay? Confusing? We have this container of gas at 300 bar. So many moles, 0.68 moles I think I said. 100 cc's. If we compress the gas to 500 bar, we still have 0.68 moles. That's it. But now we've got 60 cc's. But the amount of moles and the composition, because you guys have done flash calculations, all that matters is the number of moles and the composition you put into the process for determining the products. The two products are these. Okay? So the amount of the products is only dependent on these two numbers. Those don't change. Okay? These are constant at any pressure greater than or equal to the dew point. So this is going to be the same oil-gas ratio. Okay? It's going to be the same oil-gas ratio. This exercise, we're just taking a saturated gas to an undersaturated state. Okay, and when we do that, the composition remains constant and the number of moles remains constant. Okay? Now, the BG here will change. Why will it change? Well, the volume of surface gas from reservoir gas, that remains constant, right? Like up here. But this here is a function of the temperature and pressure. So instead of using 100 cc's, we're now using 60 cc's. So the BG will definitely be a function of pressure, whereas the little rs will not. The little rs will not be a function of pressure above the dew point. Okay.
Curtis?
Yeah.
Are the numbers constant or the ratios?
Both. Both. Yeah, because when we have the total moles entering being fixed, I mean the composition will give the ratio constant. Okay? So the ratio is only a function of the composition. Okay? That's maybe not clear. So the little rs is only related to the composition that goes into the process. Okay? But the volumes here those are related to both the composition and the number of moles that you put into the process. Okay? The number of moles, if you put in only a tenth of the moles, if you only put part of the gas into the process, then you would get a different volumes. But since we're basically down here in this cell, we're only changing the pressure. We're not taking anything away. We're keeping the same material. We're just changing the pressure. The number of moles is always the same going in. Okay. So these are the three properties of gas. And likewise to the oil, we can calculate, and we could do the material balance like I did Tuesday. The gas density at a given pressure is basically the density of this surface gas coming from the reservoir gas plus the density of surface oil coming from the reservoir gas times the little rs. It's basically the volume of surface oil. Volume of surface oil times density gives you mass, right? So this is kind of like the mass term, divided by this Bg, which is a function of pressure. So that's the equation for getting the gas density from these properties.
So the amount of the gas coming out from the oil does not impact the viscosity of the gas?
Okay, gas coming out from the oil. There is no oil here to come out of. Because we have a gas phase. We only have a gas phase here. Okay. This surface oil is coming out of the reservoir gas phase. The surface gas is coming out of the reservoir gas phase.
Sorry, didn't you say that the RS wasn't a function of pressure?
If it's together with the oil. Okay, the thing is that, like in the previous, okay, this is undersaturated condition. That's the undersaturated state. Okay. If we keep the oil and gas together and move to a new pressure, the gas composition will change. Therefore, the little rs will change. Okay? That's if you keep the gas and oil together. Okay. All right. Any other thoughts or questions or confusion?
The
Yeah.
pressure below the dew point will have one phase or
Below which dew point? Below this dew point here?
yeah, dew point.
Okay. For this gas by itself, we never go below lower pressures. Okay? Well, at least not what we're talking about here. Okay? So the way we're looking at this, we're only looking at if we have a gas phase entering a surface process. That allows us to calculate these three properties. Okay? And those three properties can be calculated at any pressure greater than or equal to the dew point of that gas. So that's what we're. So. Okay, so let's move on, and let's just look at the behavior of. Okay, we have to. Okay, talk about the gas formation volume factor. Okay. So far, I've only written BG. But there's a traditional, which means that it's in 99% of the books and papers that you will read in petroleum engineering. Okay? The traditional BG is given by this equation. You'll find it hundreds upon hundreds of times. In books. Okay?
Excuse me, Professor. In the previous equation, before you proceed, I think density of gas. If we just keep the gas and the oil together, we will have the RS as a function of pressure. What if we just treat them separately?
Okay, so what I did here is that I created the gas by taking something that was two-phase, right? So that the gas and the oil were in equilibrium. By definition, that gas is saturated at its dew point, right? Then I throw away the oil. And now I'm just going to look at that gas by itself as a gas phase. It is a gas phase at that pressure and above, right? So that's what I tried to talk about here was only for that situation. First, we have to create the gas. We did that by putting it together with some oil. Then we throw away the oil and keep the gas. Now we can keep that as a gas phase as long as the pressure is equal to that pressure, its dew point, and above. Okay? Yeah.
But doesn't gas usually condensate when you increase the pressure?
Okay. So the question is, doesn't gas usually condense liquid out when you increase its pressure? Only at low pressures. That's the if we take that gas and we look at its pressure temperature diagram, this is the temperature, let's say, in a reservoir. And maybe the critical point is over here. Okay. We've got these, so this is 0%, this is all dew point line, right? And then we've got 10% liquid. Zero percent, 20%, 30%, and so forth. Okay? So we're talking about here. So what you can say is that doesn't liquid usually condense out of a gas as you increase the pressure? It's only if you're starting down here. Yeah, and that's called conventional condensation. If you start up here and you start seeing as lower your pressure you get liquid, that's called retrograde, or the opposite of normal condensation. So yeah, you do get condensation if you increase the pressure, but only if you're at very low pressures.
So the gas table we are generating is for a fixed gas composition.
That's right. So this is the PT diagram for that gas that I created up here.
So in the reservoir we always have gas with oil, and the gas, when as the pressure decreases, the gas gives oil in the reservoir.
Well, let's not always say always, because there's not an always. In a reservoir, you might have gas, you might have oil, you might have both. Right?
And for example, if we have both,
Yeah.
and we are decreasing the pressure, then oil will come out from the gas, and its composition will change.
Yeah, but you're getting into a much more complicated application of this. So let's just first we have to understand how we get the tables. and then we can start talking about how do you use them. Okay, so let's wait a little bit on that. The point here is that this gas formation volume factor, this is the traditional. This is what you find in 99% of all petroleum literature. Okay? Is this equation. And the problem is that that is not the equation we want to use. Okay? Because this equation basically assumes that little rs is 0. That there is no surface condensation of liquid from the gas. And that's almost never the case. Okay? Where it's saying that the volume of oil from gas is 0. And it's just almost never like that. So we don't want to use this. Don't usually, there's always the exception, want to use this definition. Okay. What we want to use BG is volume of gas at pressure and temperature over what you actually get as surface gas from that reservoir gas. That's what you want it to be. We want to be relating these two volumes. Okay? This is what we sell. This is the surface gas product we sell. That is the gas product we want to be working with in our equations. If I say my well produces 1 million standard cubic meters per day of gas, I want it to be sellable gas. Okay? Not something else. At least that's usually what we do. Okay? And that is equal to, I'm not going to do the derivation for you, but that is equal to this. Okay? Which is the traditional times the moles that becomes gas over the moles that we start as reservoir gas phase. And because this number here is always going to be less than or equal to 1, I'm sorry, less than or equal, greater than or equal to 1. Right? I mean, because the amount of moles that become surface gas can't be more than what we start with. It has to be less than or equal to. So this number here has to be greater than or equal to 1. Therefore, and what we're going to call this, we're going to call this a special term. I apologize. It's going to be BGD. Okay? And I'll come back to why do we call that later. But that's what we're going to use this. So, and we're going to call this traditional BGW. Okay? It's just convention. Okay? So this BGD is always going to be greater than or equal to the traditional BG, which I'm calling now BGW. Okay? That's the traditional. Okay. You guys are engineers. You just say, Curtis, how big a difference are we talking? Okay? Don't mess with me. I got up this morning, I came to class, okay, but I'm an engineer. Is the difference a 0.5% and you're just burning our time, or is it like 8%, which, you calculate your salary and, 8%, you react to an error of 8% in your salary, right? So what is the magnitude of difference? The magnitude ranges from, this thing here is that NGG over NG, I'm just going to give that quantity, is going to range anywhere from 0.99, it could of course be 1 in theory, down to as much as 0.85 or even less. Around 1 to 15% error. Okay? 1 to 15% error. That means that we have to pay attention. And if you want just, okay, when is it 1 and when is it 15, Curtis? Okay, that's your next question. Okay? Because you want to be a good engineer. You want to just like ignore it if it's 1%, right? And you want to be really involved in this if it's like 12%. Okay? Because you don't want to make an error of 12%. Yeah.
Why is NGG smaller?
Because you can only have less moles produced as surface gas, because what you start with is Ng. Okay? What becomes gas at the surface can't be more than that, right? Has to be less than or equal. So that's why this will. It's the.
Where the rest is going? The rest is going where?
Becoming condensate. Thank God. It's now $33 a barrel. Okay, it's going up. That's where it went. We're getting more money per molecule. This is basically can be estimated if you just look at your composition, your molar composition of your gas. Okay? If you just take that number there, that's going to be this, approximately this number here. So if you've got 6 mole percent C6 plus, that's 6% error or difference. 0.94. If you got 11 mole percent, 13 mole percent like Kristen gas condensate in Norway, 13 mole percent C6 plus, then the error is big. And if you go to, I don't know, Frigg, you don't know about Frigg, that's all over. If you go to Midgard, then it's probably 0.2 mole percent C6 plus. So who cares? Okay? So basically, if you just know, if you know in your reservoir gas, or just in the gas phase you're looking at pressure and temperature, if you know that composition of the C6 plus amount, then you kind of know what magnitude of error or difference you have between using. So this is the equation we want to use. And it's equal to the traditional times this factor. Okay? Okay. Okay. So we call this dry gas formation volume factor. Why do we call it dry gas? Because we have dried the reservoir gas or, I mean, really the gas at pressure and temperature. By the surface process. I'm going to write like that, okay? To surface dry sales gas. Okay? We've extracted the liquids, which we call condensate or surface oil. Okay, we've dried this gas at P&T by processing it. That's why we call it dry. It's okay. That's why it's called that. Why do we call it up here W? W stands for wet in this case. All right? So sometimes we use the concept of a surface wet gas well stream. A surface wet gas well stream. And what is that? A wet gas well stream is the dry gas from gas volume that we actually sell as a gas, plus the condensate or the surface oil that comes from gas. But we translate that material, that barrel, first by its density to get mass, and then by molecular weight to get moles. So we convert that barrels to moles. Okay, what's actually we're getting $33 for. I don't know why we do this, but so we convert that surface oil coming from the gas to a molar amount, and then we say there's 23.68 standard cubic meters per mole. If it happened to be a gas, which it's not. But if it happened to be a gas, that's how many standard cubic meters we'd have. And that conversion, 23.68, is just RTSC over PSC. Okay? That's the wet gas concept of a well stream. Okay? Now, it's stupid because you never want that, what actually is $33 oil, to be considered a cheap $2 per MCF gas. Okay, it's just kind of stupid, but we do that sometimes. It's the same stupid that we use the barrel of oil equivalent. Am I going over time? Almost. The barrel of oil equivalent. Have you guys heard of barrel of oil equivalent? It's as stupid, but we still use it. What is the barrel of oil equivalent? BOE. Okay? barrel oil equivalent. If you're a gas country or a gas company, you like the concept of barrel oil equivalent. It's like Qatar. They have 900 trillion standard cubic feet of gas in this big field. Okay? They also have 20-some billion barrels of condensate, real $33 condensate. Okay? But forget that. And let's talk about the 900 trillion standard cubic feet of gas. Okay? The energy equivalent of one barrel is about 6,000 standard cubic feet of gas. Okay, the energy equivalent. So it's kind of an energy equivalence. And that energy equivalence is that basically one stock tank barrel is approximately the same energy as 6,000 standard cubic feet. Okay? Believe me or not. Okay, that's what it is. 6 MCF.
Is this some standard
Huh?
oil? Is this some standard oil or?
It's like the burning quality of an average oil and an average gas. I mean, it's approximately. It's like the number you need to remember. I think they use 6,000. Okay. So that if you own 900 10 to the 12 standard cubic feet of gas, okay, you can call that 900 10 to the 9th MSCF, which is 1,000 standard cubic feet, right? And then you can say, well, 6 MCF is 1 barrel of oil, equivalent, on energy basis, okay? So how much is that? You guys do the calculations for me. I'm not going to let you take a break until you do that. 10 to the 9th stock tank barrels. How many? 150. Okay, 150 billion stock tank barrels. Hussein, how many stock tank barrels do we have in the Gawar field initially? Do you know? Okay, it's around 100, I think, which is the largest oil field, true oil field in the world. $33 per barrel oil. It looks like a lot of. Okay. It is a lot of energy. Let's not joke about it. But it's you're never going to make the value $33 per barrel in value selling the gas as gas. Okay. But in terms of energy to the world, it's giving about the same. Of course, oil gives a lot of other things than energy. It gives us plastic products and all the other things that we get from oil. Okay, so that's so it's kind of a silly, in a way, not a silly, but it's an energy equivalence. And on the wet gas concept, it's a little bit the same thing. It's not something that is a value equivalence, but it's just a concept that we sometimes use. Okay, and so this traditional BG is called wet gas because it's basically saying that we put what became condensate, surface oil, we put it back into being gas. Okay, so this assumption for the traditional BG becomes correct. So this is. Okay, that is the way it's. Yeah. So you convert what really becomes surface oil into an equivalent gas, add it together what becomes surface gas, and you use this wet gas equivalent. And in that case, then this equation is correct. Okay. All right. So that's, yeah, I think that's everything. Any questions before we take a break?